morning to one and all present here today. It is my absolute pleasure to extend a warm welcome to everyone gathered here today for the fifth day of the 60th Faculty Development Program on integrating AI and ML for next generation electrical engineering solutions, organized by the Electronics and ICT Academy, NIT Warangal, in association with the Department of Computer Science and Engineering, SRM-IST, Kadapani campus. It is our great privilege to welcome and introduce our esteemed speaker for today, Mr. Jay Ganesh. Mr. Jay Ganesh is currently serving as a project lead at Warangal. His expertise and passion for driving technological transformation have made a significant impact, and we are honored to have him share his valuable insights with us today. I also extend our heartfelt thanks to all our online and offline participants for being here today. I am sure that you all will find this session enlightening and inspiring. Without any further ado, let's welcome Mr. Jay Ganesh. Thank you, sir.
அது விழுந்துருச்சா ஐயோ
Good morning, guys. Good morning.
Good morning.
Great. Okay, so welcome for the day. So today, you all here to learn about the topic. It's about what? What is the topic of today's presentation? Sorry? Not just speaking. This is a part of your session content. So what is your actual content of the day? Any idea? Sorry? Reinforcement learning. Technically correct. Anything else? Great guys. So okay, so today's your topic is all about like advanced AI ML applications. So on top of that, I'm going to cover some advanced architectures of a deep learning. And on deep learning, we have various architecture, and one of the prominent architecture is all about GAN architecture. So this architecture you might not be practiced of, but you guys have been experienced with some interesting and attractive applications which you have seen in Instagrams and some of the threads of the Twitters and some of the Facebook videos or something else. Because when I show this video, what is a GAN architecture is about, you will get to know. Okay, so GAN architecture, as I told earlier, this is one of an impressive and advanced architecture. We have a neural network for data frames and NumPy data in order to handle those, and we have a CNN architecture for images and RNN for completely text oriented. So this GAN architecture is the one we are talking about, the generative AI, right? So generative AI, one of the origin architecture, one of the prime architecture for the generative AI. In order to generate a new content, like if you give some kind of 5 to 10 images, it can able to create almost 1,000 images or 10,000 images by using those images. Simple example I'm talking about. And also, I'll talk about what are all the impressive application of this GAN architectures and everything. And of course, this GAN architecture has most relevant to the current Gen AI model we are working on. So one of the tool which most aware of like ChatGPT. So I will talk about autoencoders and variational autoencoders for some 5 to 10 minutes, and I will relate it with how it is connected with the ChatGPT or something else. Okay. So am I audible without this mic? So that's all. So in the neural network era, in the deep learning era, so totally we have a different neural network architecture, and one is about neural networks. Many neural network architectures are there. So for how we have experienced this neural network architecture, with respect to discriminations. Discriminative AI we are talking about. So if you give an image, it will take that image and it will process and it will give you the detections on top of this image. And if you give some English content with the help of translation, we can able to translate as similar to the audio. So far, in the deep learning era, we all worked on discriminative AIs. So we have two different AIs. One is like a discriminative AI, and another one is like a generative AI. So the one which we are talking about is about a generative AI. But before that, till yesterday, we have discussed about some transfer learning, SRNN you might have discussed, and everything is about discriminative. If you give some data, and you can expect some output which is relevant to the input you have given to the model. So your output is completely relying on the input you have given to the model. So this is what your architecture so far is worked on, it's a discriminative model. But today we are going to talk about a advanced AI one. So in this advanced, of course, the first architecture is a generative models. So in generative models is nothing but if you give some data to the model, it needs to pick the data and it needs to understand the data, and we are expecting the data to generate some unique content. Example, you have a neural network model, you are giving an image to the machine, and if you give an image to the machine, your neural network architecture will understand the features blah blah blah, and it will tell you it is an apple or not, and it will tell you like apple is the shape of this and apple is the texture of this, likewise this will give you some content. But when you are giving the same apple image to the generative model, what we are expecting, it has to take the image and it needs to say the apple is red in color and this is a shape of some unique shape and it has these many nutrients, and these nutrients supposed to have by the kids and the adults at the age of between blah blah blah. Likewise, it will be giving you some ample amount of narration towards the data you have. That means your output is not completely rely on your input, and it has generating the new amount of information about your input. Okay, so earlier discriminative AI just a discrimination, but the generative AI, it will be generating the new content for the input you are giving into the model. Okay, so where it is GAN architecture starts from. So GAN architecture has been started from like auto encoders. Yesterday you might have seen auto encoders, I guess, in deeper. Yeah. So maybe I can just tell very high level. So auto encoders are nothing but it is like a mainly we have used auto encoders for two things. One is like whenever you are having unsupervised learning techniques, there we will be using a auto encoders in order to extract the image informations to be applied on the latent space, and other one is compression. Whenever you wanted to compress the images, for this process we will be using auto encoder. So auto encoder is good enough to understand the data and capture it, and it will be storing it in some latent space in the machine understandable format, and it will be reconverting to the actual image. So that means you can give an image, encoder will process it and it will extract the informations in the tinier way, and it will be storing it in a latent space, and then it will be given to the decoder architecture. That architecture will enlarge your picture, and you could have asked, okay sir, what is the use of this? How this process would be relevant to the GAN architecture? So that's what we have another concept called variational autoencoder. For example, as I told earlier, just connect everything from the ChatGPT scenario. Okay, now you are having a image. So consider you are in the some latent space. Okay, so now you have trained your data set, trained your model with the dog image. So various of the dog images, and this is a latitude, and this is a longitude, and this is a latitude. Okay, excellent one. So this is your dog images. Whenever you are training your images, so this particular sample is storing the dog images. So that means you have a ChatGPT model and you have trained your architecture with the dog images, and you are expecting something to be generated with the dog. And if you are putting some questions, tell me about something a dog. Of course, your question will come under this latent space or enter into this era, and it will be generating some dog related information. There is no doubt in it. For example, you are asking about something differently. Give me generated dog image with the horse tail, with the giraffe neck. Like this, you are putting some questions. So nowadays it is not a big deal, right? So with the help of a lot of AI tools, you can able to generate a new images for this particular context. So now, if your question is all about like something different, of course your question will come under somewhere here. So if it's come somewhere here, what will happen in the sense your model will generate some noise data. That means it will be giving you this kind of ununiform informations. Okay, it will be giving you some ununiform information. Okay, so you know how they dealt in a variation not course. Okay, sir. Now you said initially ChatGPT 1 version, if it was 6, this is how they have been started their model developments. And after that, you are training your model with a lot of images like the horse images, and you are training with the some giraffe images. Okay, so what they have done in the sense, okay, you can create an architecture, but whenever you are dealing with an architecture, your architecture should be trained with a lot of images, and then it can able to understand relative combinations between each and every data, and it can able to generate the new content. This is what a content is about. So now you can ask me a question, and again the same question that the dog, the generate an animal with a dog face, giraffe neck, and as well as a horse tail. Again your question.
Sorry, sir.
Oh. So again, if your question which is closely relevant to this particular era, maybe if your question is fall somewhere here in the sense, of course your model will fail again. And if your question is fall somewhere here in the sense, maybe you can expect some unique output to be generated. Okay, think about it, how they have handled in a variation not yet code. So what concept in the sense, you can pick a sample from the distribution. These are all the distributed data. Okay, these are all the distributed data in the latent space, and you need to pick the sample from the model, and in order to pick the sample from the model, so it needs to be connected one with each other. So there is a concept called continuous region. So what is the meaning of continuous region? Since they have been connected all your data like all your data is connected in like this. Now everything. So this is a dog images, and this is your what is that? Giraffe, and this is a horse. Something. Okay. So likewise, you have created all the data in the distribution latent space, and you are connecting with the continuous region. Now your question is coming to the architecture or the neural network model, and you are putting the same question: generate an animal with a dog face, blah blah blah, and your question will fall here. And now you can able to understand your query based on the existing features, and it will generate the exclusive output you are expecting. Okay, so now, so this is what I am talking about. So whenever you are having the data, and when it is connected in the continuous region, you can able to generate everything. So now coming to the other scenario. So here, now you can completely relate the same problem statement with the so now the same problem statement. So now I talk about an images, right? So now you can consider you have a same latent space, and you have the data set is all about academics data. So your ChatGPT is trained with the academics data. So all our academics data is here, and your programming data. In order to generate the new codings, your programming data sets, and as well as in order to make it as a data. So in order to make your academics data, and I have a programming data, and all together, if you see in this case, I am trained my model with some comprehensive data. So this is how we are having the chat GPTs or any of the GPT models or LLM models, and they are training all the data in the continuous region, so that we are able to identify the relationship between the one value with the other value. Maybe this cluster is different, this cluster is different. But your question is falls somewhere closer to here in the sense it can able to generate a data very peculiar. But when you are asking your model to generate a new set of data which is not exist in the world, that means the dog face with the horse tail is not never exist anyway. So in order to generate the new content in such a way, you have, if your question is falls somewhere here, and it will be trying to identify the distance between this, distance between this, distance between this, and it will generating the new images. Okay, so this is how the exclusive concept which is used in all the generative models currently we are working with, and everything they are working in the latent space of the distribution of the latent space, and we are picking the samples from the distribution space, but the distribution space is connected one data with the other data in order to prepare the relationship between all the data. Okay, because when you're putting some questions to generate a Python code with the Fibonacci series Python code, something you're asking you about, and it will be generating the Fibonacci code from this particular cluster. Okay, fine. But in order to explain that Fibonacci, you will be asking the same question. Explain me the Fibonacci series in every line. Likewise, you're asking the question. So obviously, it is not only relevant to the Python programming; it is also relevant to the comprehensive. Okay, so now your question will fall somewhere around this region, and it will take the basic information from here, and it will take another knowledge from here, and it will generate the content with the programmings and also with the narrations. Okay, so this is a concept, the one of the base concepts how they have been used in the continuous regions of the neural networks. And now, so in specific how they are specifically and each and every data. In order to understand each and every data in the autoencoders, it will be capturing the data and it will be stored. That means some determinant values. So if you're taking one particular value, if you wanted to know about a dog, it will be creating some determined values. Determined value is a single array which determines what is a dog and how dog looks like kind of things and all. But when you come for the variation autoencoders of the GAN architecture, they will be extracting the dog images and they will be storing in such a form of mean and variances. So by using this mean and variances, I can able to understand the dog's information in the variance dimensionality. So for example, the same dog information I can store it in a two array. One which is telling you about what is the mean of the dog value and what is the variance of the dog value. Simple example, what is the average dog looks like. And variance in the sense how the particular dog is variated from the other dog. That means that is a standard deviations. So variations. Okay. So this is a value which helps to make your architecture to be trained in a well order during the time of optimization. Okay, so now we are extracting these informations. Those sample distributions will be given to the decoder and it will be regenerating the data. Okay, so now this is a one concept of GAN architecture. This is how helpful in the concept of chat GPTs and the related coordinates and the coordination and continuous region. And there were some common examples, comparisons I have posted it right here. And if you see normal encoder and as well as the variation of encoders. So in the normal encoders, it learns a hidden representation of the input vectors. That means cannot generate the new data. And what does this optimize? Minimizes the construction cost. So now, when you come for the autoencoders, as I told earlier, they have only used to for the compressing the data, not to generate the data. It will not generate any new content by using the autoencoders, and also it has a loss of reconstruction loss. That reconstruction loss is nothing but, for example, you have the lot of Google photos in your mobile phones, okay, and every data is being uploaded to the cloud, somewhere else is available. So how many of you knows about it, this concept? I think so. There is a concept called federated learning. So in your Google data in mobile phones, right, we are having a lot of data. And anybody aware of like how the Google photos is being automatically created with a lot of clusters by understanding the features of your data, because we are not labeling. Whenever you are taking the picture, you are not telling to the picture this is not a selfie. Whenever you are taking pictures some classrooms, you are not telling this is a classroom. That's everything is like a images with the non-labeled data, kind of unsupervised learning. How this kind of data is being brought into the common loop, and how they are making it as a cluster in terms of your folders. Like this pictures has been taken in some events. This pictures has been taken in some classroom. This pictures has taken as a selfies. Like this, it is nothing but it is taking your data in our mobile phones. When you are turning on the data, there is a concept called autoencoders. I mean, the simple concept of autoencoders. It will compress your data into some array of points. That points will be uploaded to the Google server. That Google server will take the data and it will understand the mean and the variance of your picture, and it will make the clusters out of it. That cluster information which is feeding back to your mobile phone, and it makes the folders possible. And the awareness and the unsupervised learning is failed to understand. At that moment, it is asking you to understand the model equipment. So this is your, just confirm, this is a face of you. This is a face of your son. This is your face of your friend. Likewise, it will ask you. Okay, so how these are all the backend. So backend, we are talking about like just Google Photos. The Google Photos, how it is compressing the data to upload it to the federated learning combinations. So one of the concept called autoencoders, and we are using the reconstruction loss. Reconstruction loss is nothing but when I'm taking the picture, I have a good pixels and I have a good variance and means of your images. But when I'm just converting them back to compressed images, I should not lose any of the information. So that means minimize the loss from loss, construction loss will be there. So I cannot, when I'm compressing it, I cannot have the same information of your pictures. Maybe I would lose something. So that's what very minimized reconstruction loss will be there. But when you go for the variation of encoders, it know how to generate the new data, and it's the minimal construction loss, and as well as the later loss we can talk about, we call it as a conversion loss. So KL loss, so KL conversion loss will be there, and the later filters are sampled from the Gaussian filters. And what is the prime differences between a GAN architecture and the variation of encoders? So that was the same. So what is the one prime point is that how stable is training? It requires finding a Nash equilibrium during the training. So it will be using some equilibrium concepts, general Nash equilibrium, doing it, right? Taking the data, classifying them, and predicting it. So same concept we are working with. And here, if you see, it is an end-to-end training from the architectures. So if you see, the output looks like this. When you come for the GAN architecture, you can able to see the sharpening, and you can able to see the edges, and everything is a very peculiar and a very neat way. But when you see the data, the variation of encoders, you can able to see the lot of noises or play around the process. Okay, so now let's move to GAN. Now I'm talking about the GAN. So before getting to GAN, back to the most if you see
In fact, this entire suite, they know are not forgotten and were created using deep learning and artificial intelligence. And in this class, you will learn how. It has been an honor to speak with you today, and I hope you enjoy the course.
Hi everybody, and welcome to MIT 6S191.
Hi everybody, and welcome to MIT 6S191, the official introductory course on here at MIT.
So this particular videos, right? The one you have seen about the Barack Obama. So this is nothing but most of you aware of what technology it is. This is called deepfake. So it is a deepfake technology, and the deepfake we are talking about a deepfake technology, and the deep learning architecture behind was helpful is nothing but the GAN architecture, generative adversarial networks, the one we are using in Google. And at the time of because GAN architecture was available long back. I mean, it was invented at the time of 2010 or 29 itself. I mean, 2009 itself. But the thing in the sense, there was no computational power, we don't have any specific configuration in order to make GAN architecture to be running in a real time, because that was quite complex architecture. It is not as simple as we are running the neural network architecture in a Cola, running an architecture in the the CN or something else. It's a very complex architecture. In order to run an architecture, you require some set of unique computation. Those computations is mandatory in order to execute the same problem and in order to execute that architecture language. Okay, so think about it. At the time of 2017 and all, the GAN architecture was started to arise. Something else, there are some papers have started to come. So how people have started to know this GAN architecture after deepfake technology came to the front. So when deepfake technology came, so there was a lot of chaos, a lot of issues which happened at the time of deepfake arises in the market. But now it's going like anything. Now it's going like a hell. So it's more. Lot of the places they are using in the beneficial way, and some of the places we are using in some negative cases also is there. So deepfake is one of a prime spot. If you ask me, there was some video. So some Italian prime minister video, right? It was posted in the Facebook, and it was a defaming other country leaders. So Italian Prime Minister is speaking about other countries' leaders in the defaming part. So that video has been removed from Facebook very instant, but Facebook taken almost some quite amount of time in order to ensure whether it is a true video or a fake video. Because if it is a morphing video, we have been practiced for a long time. So morphing video is something, but I'm speaking over here, I can take some of your face pictures and I can paste it on top of my face, and I can able to make it much more exclusive using some augmentation techniques. But when you come for the GAN architecture, it is not related to that. So what will happen in the sense, I'm taking my facial landmarks. For example, if I have my face, I'm talking in the sense, I can able to take the entire facial landmarks of mine, and I can take that landmarks alone, and I can place it on your faces. So now, placing on top of your face, what will happen in the sense, I'm not changing the face attributes of yours. I'm just changing the pixel values in order to make to talk. So for example, you are standing as a picture and I'm pasting my facial landmarks on top of your face, and I'm just adjusting your lips, adjusting your eyes and adjusting your jaws in order to make you to speak. So this is how GAN architecture was most familiar, and also because nobody could able to understand, it's not easy as easy to think about to identify whether it is a morphing video or it's a original video. So nowadays, even if the original videos are coming, people are saying it's a deepfake videos. Okay, so that amount of capability that deepfake is there. Now it's a cup of tea because a lot of tools came actually. First of all, a lot of tools came in the market, but now up to some seconds only can able to do it. And if you wanted to make by using this deepfake technology for the entire movie, of course, in near future we can able to experience that one. Maybe we can see our most impressive characters in the movies like a Paul Walker. Maybe in the near future the Indian actors would come back again in acting in the same movies. Of course, it will happen for sure, because I was talking about this from almost 6 to 7 years back. But now almost most of the things have started to come. At the time of maybe 10 years, we can able to experience it. But the problem here is we don't have a capabilities. We don't have a configurations available in order to make such movies or something else. Yeah, of course, like Avatar 2, right? In Avatar 2, there is a second phase. Specifically, second phase, the entire ocean-related pictures, and everything has been created by the GAN architecture. So we are talking about like a CG box. So what is that? Computer graphics. But the real thing is nothing but everything is based on architecture. Okay, so let's move to the topic. So now let's move to GAN. And if those videos are not makes you surprised, of course this particular picture never makes you surprised, because these are the simple portraits and you can take us 10 frames maximum enough, and you can take any facial landmarks which is speaking in this particular angle, and if you are taking the same facial landmarks, you can take my facial landmarks and you can adjust them and you can paste it on like you can able to make any beautiful Mona Lisa and Albert Einstein to talk. Okay, and if you ask me, okay sir, today we are doing hands-on, is it related to anything this deepfake? Yes, I have one hands-on related to the deepfake, and I'll teach you. You can do something else, but with respect to Google Colab, you can able to do up to 8 seconds of video or 10 seconds or 20 seconds of video maximum. It's not possible. And in order to make that deepfake technology to make it alive, you have to do a lot of pre-processing. Okay, I'll tell you everything what needs to be done. And also, one of the prime hands-on is all about generating the samples, generating the fake samples. So that is a one prime hands-on I'll show you. First I'll show you about deepfake and then I can go there. Okay, now we can talk about the interesting concepts of the GAN architecture. So what is this architecture is about? Nothing but your GAN architecture is a combination of two architectures, two neural network architecture. One is called a generator and another one is called a discriminator. Your generator will generate the samples, and your discriminator will discriminate the samples whether it is a true or not. Let's consider we are the GAN architecture. I am a generator, and you are the discriminator. I'm generating the new content and I'm giving it to you. Okay, so now you are discriminating that we are comparing with the ground truth data, and you are saying this is not a true data, and you are giving back to me. So likewise, these iterations will go forever in order to generate a new unit. So this is a similar hands-on. This is the same hands-on we're going to see, guys. Hold your horses for some time. So that's what I posted a video in order to bring you back your attention. But you're seeing the video. After the video is gone away, you're going back to the normal state. How many videos I could post? For the entire session, I cannot post the whole videos. Alright. Okay. So coming back to the normal. So now this is a similar hands-on we're going to see it now. It is about a GAN architecture with the hands-on of generating the fake samples. So this particular project we're going to see, right? It is completely your potential. How are you going to use this hands-on? This hands-on is you can take it for any of your that's what as I told in the previous session. I'm not sure. You can use it for your final projects, mini projects, and you can take this project and you can mutate some changes, and you can nominate yourself to be participated in some of the IET conference or the IET meetings or something else. Yes, because this is that much of research is going on top of the GAN architecture. If you make some slight changes, or if you are making some unique applications over the GAN architecture, you will have a great future among the academics. You can go for like presentations and projects or something else, everything you can do. Okay, the hands-on which I'm going to show you, it's very useful. Up to this is in your hands, how are you going to take it? Okay, here I'm just telling this one. Now we can go for, as I told earlier, we have a GAN architecture with the two architecture parallel. One is a generator and another one is like a discriminator. So in generator, I'm going to give this noise data. Consider I'm a generator. I'm going to have only the noise data, which is not even aware of what I'm going to generate. Just I'm having nothing data, just a noise data. And discriminator. In your discriminator, I'm going to give the ground truth data. So you are the discriminator. To the discriminator, I'm going to give the ground truth data. That means actual data. So now I'm going to predict the data set. This is how your data set looks like. So likewise, 60,000 pictures I'm going to give it to you. Now what I'm going to do, this is my model distribution. Initial way, I don't have any knowledge. But this is my target distribution. I need to achieve this target distribution, or else I need to match closely related to the target distribution. That was my primary model is about. So first a few iterations, maybe up to 50 epochs. Maybe we have a 50 epochs, 10 epochs. I am able to try to understand the data. I'm trying to copy some data which is relevant to the ground truth data. So how the communication happens is nothing but I'm a generator. Just to consider I'm a student, and you are the discriminator, and you have a ground truth along with you, and you are the master. And I'm generating the new content, and you are comparing with the ground truth, and you are giving this is not actual data I'm expecting. You are giving the feedback, and you are doing the back propagation along with me. So by taking that weights and bias, I'm just retuning myself again. And I'm giving the other set of data, and you're comparing and you're giving. So this iteration will go until you are getting the exclusive result of what you're expecting. Okay, we will be setting some threshold. Up to reaching the threshold, we are doing this iteration of long forever. Okay, so this is your generated data, and this is your discriminator is going to have a ground truth data, and we're going to compare our ground truth data with the generated data. And first few attempts, we are generating some new images, which is trying to understand. And then after some latest attempt, we're trying to understand some new data. This is about your GAN architecture is working, and the same hands-on I'm going to show you now. So I have a 50,000 of pictures. By using that 50,000 of pictures, I'm going to generate 100 new pictures. Okay, you can use the same source code to generate the multiple pictures, but it's your case, and I'll tell you how to use and how to mutate the source codes. Okay. So now, is it clear, right? This particular thing is clear, right? So because when I'm explaining the code or the hands-on, that will be helpful for you to understand much. Okay. So now this is a basic generation process which we have already seen. So this is how your basic framework of your architecture. So one is about like your rated space, the Z data, and you will be giving it to the generator. So this generator is a one generating the new data, and it will be generating the fake samples. It will be generating the fake samples. That fake samples will be given to the discriminator as an input. Okay, your discriminator is also have a discriminator. Consider you are the discriminator and you also have a ground truth data. This is a ground truth data. So now you are comparing with this fake data with the ground truth data and you are giving the results. If your results are matches together and you will be generating the new data. Okay, so this is a framework process will happen. It's a top level framework, and you can ask, is this GAN architecture is a new architecture or unique architecture or unique activation function, anything we have seen? Nothing unique. The concept is unique. So GAN architecture is nothing but it is a couple of two architecture. Okay, couple of two architecture. The architecture is a complex. This architecture is complex. It's not like a CNN. It's not like a neural network or something else. Okay, so everything is the same. Architecture, what you have seen up to R100, everything is same. But here we are going to club two architectures together. We are going to manipulate them to be achieved some set of unique outcomes. Okay, so this knowledge you supposed to have what we are doing on top of this. And this is more of like equation related, but I don't want to go much equation related. It's nothing but top level I'm talking about. You are having a discriminator ground truth data. They are giving the ground truth data. You will be getting the probability distribution of discriminator result d of x. And when you are giving the same architecture flow, fake data, some noise data generated, fake data generated, that fake data is given to the discriminator, and you will be getting the output related to the d of g of x. So d of g of c. This is a probability distribution of generated samples over discriminator. Okay. So yeah. So this is about the loss calculation. Yes, as we told earlier. So here also we will be doing the loss calculation. The loss calculation is depends on your generator and depends on your discriminator. Okay, you will be having a separate loss calculations for the generator by using some mean absolute error, and you will be having some loss calculation for the discriminator absolutely like a mean absolute error or mean squared error. And this is the equation looks like. Okay, your discriminator plot is based on your real data and as well as fake samples. So all together we will be having a discriminator loss, and the generator loss is based on only the generated samples along with the fake data. Okay. So however the back propagation will happen, the back propagation is happening within each architecture. With generator will do its own back propagation, and the discriminator also will do its own back propagation, and you will be giving me the feedback. That means the back propagation will happen between discriminator to generator. So that means 3 level of back propagation will happen when you are working on a GAN architecture. Think about it. You have a simple neural network architecture and you are running for 50 epochs. It will be taking some quite amount of time in order to execute, in order to run. But when you go further, you are running the two architecture, two different back propagation, and between them there is another back propagation. Think about how complex and how the computation and the overfitting issues and everything is manageable between this architecture. Okay, so it's quite hard to manage the overfitting and underfitting issues between this architecture, and this is a base of your base knowledge is required. So when you are getting some results, you will be understanding the laws and everything, and you will be computing. Okay, so of course when you are working on a GAN architecture, you should not be lenient to your architecture. If you are constructing the GAN architecture, if you are constructing the generator more powerful, and similar way you have to construct the discriminator also so powerful. The reason is nothing but, and then one day it can able to compete one with each other. Okay, so generator is a more powerful, and you are making discriminator architecture is a very less architecture. This is your model will fail because the discriminator also supposed to be more powerful. Having said that, I don't say the generator with the 100 hidden layers and the discriminator also should have 100 layers. I don't say that. If generator is most powerful part under 100 layers, discrimination you supposed to have at least 10 hidden layers. Instead of keeping a 10 hidden layers, if you are making 2 hidden layers, 5 hidden layers, your model will fail. So this is what I'm talking about. The both of them should be in the both capable. Okay, so this is the one part you have to focus on, and the GAN architecture, as I told earlier, still there is a lot of researchers and a lot of habituals is happening around this GAN architecture. And if you are doing any projects or if you are creating any paper presentations or something else, you have a lot of opportunities get selected in the paper presentations or the project presentations or whatever it is, because this architecture is not being worked on with a lot of engineers or a lot of doctorates or the reason is it will be taking a lot of times in order to create a paper, in order to create a project or something. And it is your capable how you can able to utilize the source code of mine to do some project or to do some paper presentations. Everything is in there. Okay. So initially, because I was working on GAN architecture from 2017. At the time 2017 and all, I don't have any resources in order to make this architecture to work on, because up to 2017 to 2018, I was just working on the ground level work of the GAN architecture. We were hunting for some of the powerful CUDA engines. At the time, the GeForce engine came into the market. So we have used the GeForce engines and we have run architectures separately, and we have taken those results and we ran them separately. So likewise, a lot of manual efforts we'll be doing on top of this GAN architecture. But now we have a lot of powerful CUDA engines and as well as the A100 series and AMD, RTX, RTX engines and everything which came now. We can able to run all of them together, guys. Good, fine. Okay. Just I give 2 minutes halt. You understood? Okay, perfect. Guys. I can understand because I know how hard it is. Because why am I not shouting, and why am I not? Why you are not listening this? This is your future. This is your going to lift your future. Like I never said it, because when I was a student, I was doing a lot. I'm not having a 0% quality to talk about, to shout at a students. That is what I'm talking to my ma'ams also, professors also. Ma'am, I never shout students, ma'am, because I'm not 100% eligible. I'm 0% eligible. That's what. Just give a pause, guys. Please come. You can talk, but with a low volume. Okay. But anyway, I have a mic. I never deal about that. That's what. You can do the work, but little work. All right. So this is the reason. Now, a lot of researchers and a lot of papers and a lot of concepts came around the GAN architectures. Okay, but still now there is no equipped applications. There is no still equipped some papers or something. Okay, and so we have a multiple GAN varieties. One is a DC GAN. It's completely based on convolution GANs. So we'll be using a CNN architecture as generator, and the CNN architecture is the discriminators, and another one is like a conditioner. So whenever you wanted to generate the images, and you are giving some specific unique features you wanted to generate. Now if you see, you have a generator and you are giving the conditions as like a male, blonde hair, black hair, blonde hair, makeup, sunglasses. So now your architecture will generate the images by comparing, by matching with this feature comparison. So by using this y hat values, y dash values. And also you are generating the outputs. That outputs, when it's making to compare on top of the discriminator, it will provide the same conditions on right here. Because this sample should be compared with the similar feature samples, and it will be comparing also. Okay, so that is what we are using the conditional GANs. In our source code, I am going to teach you, right? It is all about generating the images. But in the same architecture, I can also give the condition I wanted to generate only some images of 7, only images of 6, only images of 5. Likewise, I can able to compare. So now you are having the bidirectional GAN. So this bidirectional GAN is nothing but you can able to generate the same things, everything. But when you are giving the ground truth data, you are just extracting the features of the ground truth data. They are giving to this in order to make your architecture is fast. So if you see that, right, every architecture is not created by super premium authors or super premium or doctors or something. Everything is created by some normal research scholars and normal students, normal papers. So now in this condition, initially there is a vanilla GAN which is connecting your neural networks as a generator, neural network layer as a discriminator. And these are all the things which been created by the lot of research scholars and the doctorates and the professors. And you also can create your own architecture in the name of like a linear GAN and non-linear GAN, like everything you can want. Okay. So now GAN model definitions. Yes, if you wanted to generate a new samples which is relevant to pandas data frames and which is relevant to what is that NumPy or something else, you can use neural network as a generator and a neural network as a discriminator. And if you wanted to generate any text related contents, you can use RNN architecture as a generator, RNN architecture as a discriminator, and the similar way for the CNN. When you wanted to generate a new images, we will be using CNN as a generator and as well as a discriminator. Okay. So, what is the GAN trail works? is the equation part. I hope that you are not much interesting on this case. Let me skip over. So these are all the common applications of the GAN architecture. So one is about like a phase generation. So this is what the people have started to understand, like deepfake technologies generated phase. There is one website called actually the phase does not exist.com, I think so. That is one website. Maybe you can just try it out. It will generate a different phase which is not available, which is not exist in the world. Okay, it will generate different phase. Each and every refresh you can able to use a different phase, and you can able to give some conditional caps. You can able to give some condition where you want to generate male images or female images or voltage images or something else you can able to generate. Okay, and another one is like a domain translations. So domain translations is nothing but so the domain translation. So the domain translation is all about whatever applications you have taken. Maybe I can take one example. Michael Kors, backend, this kind of wallet and the back creations. Now they are using GAN architecture to create a unique product to sell the market, to sell into the markets. Okay, and also the gaming fields. The gaming fields GAN architecture plays a vital role in order to make them online. And next one is like an aerial to map satellite pictures and creating the vlogs, and you are seeing the roads and everything, right? So everywhere we are seeing the very equipped results nowadays. The reason is one of the architecture we have been used of them is the GAN architecture. Okay, so now other one is semantic image synthesis. So this is the one thing, and another one is like the super resolution. For this guys, for super resolutions or not, we can go for CNN architecture and some of the pre-training model itself. But if you wanted to use a GAN architecture, you can able to use, but the based on application, but the based on your problem statements will be. Okay, and so these are all the some papers which I have referred in order to create this PPT and the blogs and everything. Okay, let me take you some hands-on. It is your break. Okay. Okay, guys, you can have a break and you can come back. GAN architecture is a technology called deepfake technologies. It's in order to make you guys more understandable, to make you guys make it an interesting way, so that I'm just presenting this hands-on with you. Or else maximum I will not take this hands-on as a first place. Okay, nothing but this is my repository. So this is my GAN repository. Guys, shall we begin? Okay, so now this is my GAN repository. So if you go to my repository, you can able to find the repo name called GAN deepfake. So from this folder, from this repository, you can able to find the source code name called GAN network updater. So GAN network updater, this is the source code we're going to load and we're going to practice now. Okay, so this is your repo name. Under this repo, you can able to find the source code called GAN network updater. And you can just load this source code on a GitHub repo. And before this, in Colab, and before this, you can able to find there is a checkpoints available. So what you have to do is you just download this checkpoints which is available in the drive. It's open for everyone. You need to download the drive. So you need to download that checkpoints, and you have to upload in your repository. Sorry, in Google Drive somewhere else. Download this drive path. Download the checkpoints from this drive path and keep it in some of your drive. Okay, reason is nothing but this is a checkpoints which helps to understand the latent space of your phases. This is a checkpoints. So in order to understand the latent space of your phases, we have a latent common features. So those features we will be having it in the name of checkpoints path. Okay, just download them and keep it in some Google Drive, some particular path. Okay, I'll tell you how to navigate that. So again, once again, I repeat, this is a repo name, GAN deepfake, and from this repo you have to load the source code of GAN network updated, and from here you can see the drive path. So download the checkpoints from the drive and keep it in your local Google Drive. Okay, now if you see the hands-on, so here I'm going to use, this is your hands-on account. Here I'm going to use so this is my driving video. This is my target image. So my motto is all about nothing but I need to extract the facial landmarks of this video and I have to paste it on top of Putin's face. So now I have a Trump's face. From the Trump's face, I am taking the facial features and the facial landmarks of these faces, and you can able to see almost both the frames are almost similar. That means face-wise they have a common similarity. So that I am taking that landmark and I am going to paste it on top of the Putin's face. This is a motto. Okay, now you can see in the bottom. I have done the same. So I have taken the facial landmarks of the Trump's face and I am pasting on top of the Putin's face, and the final driving video you can able to identify it. Okay, this is a GAN deepfake because here I can able to play a maximum 10 seconds or 12 seconds. Beyond that, it is quite possible. If you wanted to do that, you have to keep driving videos more than like 1 minute or 2 minutes if you are taking the, since it is possible, but it is not as easy as okay. And you can also include some audio. It is possible, but I was not included here because I don't have the snippet available. Okay, you can also include the audio after downloading this video. Okay, now in the same source code, I will try with the different data set. I will try you with the different data set. From this folder, right, you can also see base source data set. You are also able to see there is a folder called base source data set. Here I am taking the data set, I am taking someone's face, like whose face you can take. CM case. Tamil Nadu CM face, I am taking it. I am just looking at this face. So instead of Putin's face, I am replacing with Tamil Nadu CM's face. And I am just making the deepfake video now. Let it run for a while. It takes up quite a amount of time. And also it is not exclusive GAN architecture we are talking about, it is a combination of GAN architecture and some of the essence of OpenCV. From using the OpenCV, I am understanding the facial features on the every corners and everything, and I am using the GAN architecture in order to synchronize both of them together. But it is not exclusive GAN architecture because we are not able to make this kind of videos by using GAN architecture using Cola. Okay? Cola will allow, but thing in the sense with the free version we cannot even run more beyond. In order to generate this kind of video to happen in the sense, we will be taking some 30 minutes to run frequently for a few frames or few seconds of videos. So that is a complexity. Now this is my driving. So this is my driving video, and this is my driving video, and this is a target path, target image to CM's face. And now you see there is a phase differences are there, right? Because this phase is very close and this phase is not that much close, and I have a far differences. Okay, if I have a very exclusive phase to capture the sense, maybe I can able to make it now much more. Now let me make it synchronized. It will take some time anyway to load. So now checkpoints load is here. Now I'm generating the video after making animations. So here you can see I have uploaded the new image as a target image. Now I have taken the facial landmarks of the Trump space and I have uploaded it on top of the CM space. So now you can try with any kind of physics. And all you need to do is nothing but you have to apply some voice over so that you can able to make this video to talk in a real time. Okay, so that's what up to few seconds, maybe greater than 50 seconds also it is possible. 15 seconds, not 50. 15 seconds also is possible, but thing in the sense you have to make sure whether your Google Colab is supporting till the thing. Okay, so some of the scripts is a very common scripts, a very template. So maybe I can just explain with the snippets. This snippet is nothing but it is understanding your video and creating this picture. And the next one is this is a main code, understanding your key point deductions by using this key point deduction and making animations. That's it. Simple word. This is what we are doing. Everything is a library. I am not doing any hard level source code or something else. Everything is a library I am using directly here. And some of the functions I have written in the name of make animations to understand this facial features to map it out. Because I have done very base level. Maybe if you wanted to use the same source code and if you wanted to make any additional level synchronizations in the same, you can able to do and you can able to make your projects. Okay. So this is a one thing for deepfake where you wanted to use a GAN architecture. இப்போதைக்கு அதுல இருக்கிறத கொஞ்சம் சொல்லி யூஸ் பண்ணுவோம். இந்த கோட் ரன் பண்ணணும். டவுன்லோட் பண்ணத அந்த அப்டேட் பண்ணுங்க. சோ ரன் பண்ணும்போது தான் டைப் பண்ணுங்க. Okay. So now let me go to actual hands-on of GAN architecture. So this is about the deepfake technology in all the things because if you want to use it by something else, guys. Alright, so now let me go to so the GAN architecture. You can able to find the source code called repository name called GAN model MNIST. Under this GAN model MNIST, you can find 3 different data sets. So generating the GAN architecture, generating the different images for 3 different images. One is for MNIST dataset. This is nothing but one-dimensional array. So this is a grayscale images. It's not like a what is it? Different channels. And another one is like a C14. It is a color image based. And the third one is like a dynamic data. So my own car data, I'm going to create a new car image. This is what. So now I'm going to explain you about the MNIST dataset. So how we can use the images of the MNIST dataset by using the grayscale images to create the new images using the GAN architecture. So now if you go to MNIST, you can able to see the same multiplication of the data, and the data multiplication I have done with the multiple GAN varieties. So vanilla GAN, DC GAN, conditional GAN likewise. Here I choose vanilla GAN. So because vanilla GAN is a flavorless GAN, it is a very straightforward GAN. Once you understood this GAN, you can able to understand any of the GAN architecture. Okay, this is a very base, and if you understood that all the GANs are as simple as simple, and almost everything is the same. Some minor changes with respect to the architectures I might have done, but everything almost looks same. Okay, so now please load this source code. Please load from the GAN model MNIST, the folder called MNIST, and under this you need to download the vanilla GAN. Just load the vanilla GAN right here. In your Google Colab. So let me also load the source code. So you have to load CAN model MNIST data set. Here you need to download. Here you have to load vanilla CAN. So let me do the same. So just CAN model MNIST. Here I choose So before I explain the source code, I will show you the output first so that you can able to understand what is the purpose of the source code. Let's connect with the GPU so that your execution will be faster. Let me connect. So let me connect with the Okay, let me run this code. As I have shown the presentation, seeing on this section, you can see in this file section you don't see any specific folders apart from sample data. Now there will be one folder which is generated in the name of samples. So here we will be having all our data generated. I will show you that. So let it run for some iterations. Okay, so now, as I have told earlier, with respect to the previous presentation, our hands-on is all about I'm going to have two architectures. One is a generator and another one is a discriminator. Okay, so generator I'm going to give the noise data as like this. To the discriminator I'm going to give the ground truth data as a MNIST data set. Now for the few iterations, I can able to see the output is forming in such a way. Your architecture is trying to understand the ground truth data as like MNIST data set, and after latest update you can able to see the data is trying to understand in some decent way. Okay, the same practices we are going to do it here. Now here if you see the output, first iteration. Okay, during the first iteration, your GAN architecture, I have given the noise data to the generator and it is not trying to understand anything. Everything is a noise data for 0th iteration. Your architecture was not even having any idea, or don't even have any idea about what it is going to generate, and everything is like a 0th epoch. It is totally a noise data. So when you go to the epoch 1, your architecture is trying to understand some amount of information. So now I'm generator, discriminator, the generator is not having any of the data. Initially I have a noise data. That's what we have seen in the epoch 0. And in epoch 1, okay, you are giving some feedbacks, discriminator giving some feedbacks. Based on the feedbacks, I'm trying to understand or trying to generate some data. Now if you see this is the output, I'm generating 100 different images. That means 10 cross 10. So each and every images is like a separate images. It's not an overall image. Each and every image is recreated. So this is a 10 cross 10 array. Each and every array will be having a unique values. Okay, so now generating 100 samples, and if you wanted to generate 1000 samples, you can able to do it by changing the resolution of this picture. I'll tell you how to do this in a minute. Okay, this is a 1. So this is a epoch 1. So now epoch 2. Now this is a epoch 2. In epoch 2, you can able to identify some relevant information is being found. So in 0th epoch, whereas there was nothing learned by your GAN architecture, and epoch 1 is trying to understand something, but it's still noisy and still clumsiness. And in epoch 1, there was some numbers which is showing as a reasonability. 4th epoch, at the 4th epoch you can see some meaningful numbers, and still you can see some noises across the every areas. And in the 4th epoch, 5th epoch, 6th epoch, 7th epoch. So now you can see 6th epoch you have some decent good numbers, and when you go for like the 7th epoch, there was some noise. Nothing but this is like a overfitting issues. Maybe your model has been underwent through the overfitting or underfitting issues, so that you can able to do a lot of noises and some of the numbers are continuously. And the next one is like sorry. Sunny epoch. 4th epoch. So this is a new epoch. So 12th epoch. During the 12th epoch, your model is learned something. It's from 0 to 12 epochs are run. So I have triggered my architecture with the 50 epochs. It will run for almost 30 to 40 minutes. It will run in order to generate all the images. So in the 50th epoch or close to 40 to 50th epoch, if you compare, you can able to see some exclusive results is being generated by using the GAN architecture to match the MS data. Okay, is it clear? What is the problem statement is clear, right? So for the same source code, you can utilize for any of the GAN, any of the data you wanted to generate. Okay, because if you see some of like I have worked with the C40 data. This is like a color image. This is not a color image. This is a grayscale. And if you wanted to use the same source code for the color image, I have the same source code. Let me see for it. You can try that out. Nothing differences much more now. No differences. Only the channel differences will be there, and the architecture complex I have been increased. That is the difference. Now let me explain the source code. So in this source code, so in this source code, in this GAN architecture, so last time when I'm explaining you the architecture, it is more or like a TensorFlow. So here I'm going to work on with the PyTorch. So PyTorch is a other framework where you wanted to play around with the neural network architecture or the deep learning architecture. So it's one of the popular frameworks is like a TensorFlow, Keras, and as well as a PyTorch. So where we use PyTorch and TensorFlow instance, TensorFlow generally when we are working with the large scale applications, when you wanted to play around with the sequential API scenarios, there we will be using TensorFlow. So when you wanted to work with some less weight applications, so small applications or less weight models you wanted to develop, of course PyTorch is one of the key in order to work with the same particular problem statement. But what is the high benefit of using PyTorch in the sense? In PyTorch framework, they will be providing you some option in order to define some weights and as well as a bias to be tuned during the time of training. And also functional API is possible. Okay, that means it's not mandatory you have to construct the architecture one after one. And you can able to take the hidden layer 1 information and you can give it to the hidden layer 4. Hidden layer 4 information you can give it to the hidden layer 6. Likewise, you can able to mutate them and you can also able to give multiple inputs to the GAN architecture. Not GAN architecture, any of the neural network architectures. And when it comes to the TensorFlow, it is not possible. But functional API is now possible in the TensorFlow, but not as much as equipped in PyTorch. Okay, and also in TensorFlow, it is a quite complex architecture. Whenever you wanted to work with a complex architecture, TensorFlow is the best option. And now, let me start with the PyTorch. So I have some PyTorch inputs, guys. Okay, so now I have some common inputs like a PyTorch vision. From PyTorch, I'm importing the neural network architecture, and from PyTorch, importing the neural network architecture. NN, this is nothing but neural network architecture and its functional properties. I'm creating an object for it. Okay, next is nothing but it is all about utility function of the PyTorch. What is a data loader, data set, transform, save image. I will tell you like where we are using this function. And next one is like a very basic utility functions called numpy, data time, and OS and everything. Now, here I am creating the object. I am creating some global variable in the name of. I am creating the global variable in the name of vanilla cat, and I am creating the device object. This device object is nothing but this is defines your architecture should be run on CPU or GPU. That you can able to define it. So this is a function torch device. I have a if torch is connected with the CUDA server, the sense connect with the CUDA, or it's run with the CPU. Likewise, I'm creating the object for the server and the configuration. So when you are running with the Google Colab or when you are running with the local, this particular thing will help you to understand and where you wanted to deploy your architecture. So now nothing but now I connected with the CUDA server anyway. Okay, so that's what my object is created for the CUDA. Now my device is object is like a CUDA object. Now next one is like a snippet. This snippet is nothing but get sample images. I don't want to go each and every line. What it is doing in the sense, you have seen the output, right? You have seen the output. In this output, we have created one template. The template size is nothing but the canvas size is nothing but 280 cross 288. The canvas size is a 280 cross 280. And overall, I have generated 100 samples. So overall, I have generated 100 samples. Each and every sample is the resolution of 28 cross 28. So that means 100 samples I need to accommodate all this canvas of 280 cross 280. So this is what I'm creating the images. Okay, so image size is each and every image is a 28 cross 28. So our MNIST data set image size is like a 28 cross 28. So each image size is like a 28 cross 28. Okay, and the next one is I'm just titrating. So each and every cell I'm generating. After generating each and every cells, I'm just concatenating them in order to make this canvas to be shown as an output. Okay, this is a simple snippet in order to create this canvas to show your output. Because when it is generating, it will generate each and every image in separate. So I'm just accommodating each and every one. I'm concatenating them. That's what you can able to see this function. I'm concatenating each and every pictures 28 cross 28. I'm concatenating everything. I'm accommodating in this. This is a snippet which is doing that. Now let me go to the next one. So now I'm creating the discriminator. Here I am creating the discriminator. So discriminator, as you know, we have a generator and the discriminator. First we are creating the discriminator. Let's consider you have a generator here and you have a discriminator here. Just to pictorial representations. This is your generator and this is your discriminator. So initially we are constructing the discriminator and inheriting the functionality called, inheriting the class called neural network.model. Inheriting the neural network properties right here. And now in this function, in this initialization function, the constructor, you can able to see input size is a 784 and the number of classes is a 1. So input size is a 784. 784 input neurons and the output is like a 1 because we are going to finally generate one image and we are going to say whether it is a original image or a fake image. So that is a motto of your discriminator. So that is what we are having like a one neuron as a output layer. Okay, and now I am creating the super function in order to inherit the properties of this particular class to the neural network architecture. And now self.layer, sequential layer. So this is a layer called the sequential layer as I have shown in the last session, right? Sequential API, and I have a linear input. So I am creating the linear layer. So it's nothing but it is a dense layer which represents the tensor. So input size is a 784 and the next one is a 512 neurons. 512 neurons hidden layer 1. Okay, likewise leaky redo. So what is a leaky redo in the sense? In the last session I have spoke about redo function. So redo in the sense it will accept only positive values. It will not accept any negative values because in architecture we don't want to pass negative values because I don't want to make my architectures to confuse since it is a discriminative AI. But once you step into generative AI architectures, since from RN till all the GAN architectures we are working with, I mean the generative models we are working with, everywhere you have to consider the negative values. If you wanted to consider the negative values, we have two different functionalities. One is like a tan h function, -1 to +1, and another one is like a leaky ReLU. So leaky ReLU is nothing but instead of considering all the negative values, 20% of the negative values are considering negative. So that is what leaky ReLU, which represents right here. So that is what I am using the leaky ReLU as the activation function. And the next one is leaky ReLU. Next one is like a linear layer with the 5 volt 256. So 5 volt 256. Hidden layer 2, hidden layer 3. Next one is same leaky ReLU activation function for them also. And finally, linear layer 256, hidden layer 4. Hidden layer 4 and number of classes are 1. So now if you see this architecture of a discriminator construction is done and I am using the sigmoid activation function. Sigmoid activation function as it is like a binary classification. Your discriminator finally is going to say whether it is a original image or a fake image. This is what is going to say. Your discriminator is construction is done. Next I have a simple forward method in order to make this layers stable. It is a function. This is a predefined functions. Now, generator. Now, if you go to the generator, you can see the comparison. So now in this generator, you are having the function class called generator, generator model I'm inheriting. Next one is again creating the constructor. So first input is like input size is 100, input size is 100, input layer. So number of class, that means output. Number of class is like a 784. 784 output neurons. So now you can ask me what is the defined for 784? So what is 784 represents? Here input, here is input is the 784, the output of the generator also 784. That means it's nothing but you reach in every picture of the MNIST we are generating, right? That picture size is nothing but it is a 28 cross 28. So 28 cross 28 is a 784 pixels. Each and every pixel information you will be having in each and every neurons. Okay. So now we have a 784 neurons. That 784 neurons input will be connected to the discriminator. Okay, now your generated images of the MNIST image. That MNIST image will be given to the discriminator. Your discriminator takes that image and it will be processed. Okay. So now you can able to see there is multiple layers are there. So linear layer input 120, 128, blah 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 many things. So as like discriminator. But the main point you want to understand is like a batch normalization. You can able to see I have used almost 3 batch normalization because my generator architecture is quite complex when compared to the discriminator. Discriminator is just going to discriminate. But whereas generator is a quite complex architecture to generate new images. So it is required high number of layers. In order to, during the high number of layers, due to the high number of layers, we need to make your architecture more stabilized. So that's what I told you, right? In a 3 hours, I cannot take all the content in a only one stage. I cannot able to take. I have to provide some breaks. So that breaks makes you to enumerate, to bring you to the concept. The same way the batch normalizations will do. Batch normalization is nothing but during the time of this activation function updates, it will be updating the batch values. And based on the batches, it will normalizing your entire architecture values. Okay, it is normalizing your architecture. In simple words, it's normalizing your architecture during the batch evaluations with respect to the activation values, with respect to the activation function values, in order to make your architecture reasonable. So that's what. Your more architectures became complex, you must include some batch normalization to make your architecture to be more stable. Okay, and the next one is final output layer, right? So output layer is a 784, and there I am using a function called tan h function. So rest everywhere I am using the linear leaky ReLU, but here I am using as a tan h function. That means I am just giving all the negative values about one images and giving it because in order to generate a new images, I should know about the end-to-end information of the images, and then only I can able to generate new images. That's what I am considering all the negative values and I am giving it to the discriminator. Discriminator will be handling in a different unit. Okay. So now a construction of the generator is also done as well. So here the forward function in order to trigger this architecture to pause. Now your architecture is done. Now what we have to do? Now we need to give the images. Now we need to give the inputs, and then we need to define the combining methods like a what loss function, and we need to define what is the optimization functions and how many epochs. These are the stuffs we have to define before you kickstart your architecture. For that, I'm defining 100 as a noise. Noise data is 100, just random 100 data. Okay, not 100 arrays. And I'm creating the object for the discriminator, and I'm creating the object for the generator, and I'm telling to my architecture, this architecture should run on device. That means the CUDA device, which device is connected. And the next one is a transform. I'll tell you what is a transform. And next line, if you see, and if you see, I'm downloading the Minst dataset, downloading the Minst dataset from the benchmark folder of PyTorch. So in each and every framework, they have their own datasets, benchmark datasets. So TensorFlow, they will be having like a memories dataset, the PyTorch, and the C for 10, C for 100, and the Coco. Likewise, some of the dataset which is available inside benchmark dataset. Likewise, your PyTorch also is having some, by default, there are some benchmark datasets. So from the PyTorch itself, I'm downloading the MNIST dataset. So that's what dataset. Download MNIST dataset from the folder of this PyTorch, and the trained one. Yes, I wanted to download the trained values of the MNIST dataset. I'm just mentioning transform. So before you download, I wanted to transform it. So what is this? Nothing but before you come into this session, you have some prerequisites about like a deep learning, something else you have to know, something about machine learning. Same way, before I'm downloading this dataset, I'm just telling to my model I wanted to transform the datasets. Which way I wanted to transform? Into the tensor formats. So instead of keeping the data as an image format, I wanted to convert them into the tensor format. That means like nothing but it's a NumPy array format. Okay, NumPy array format. And also I'm just defining the normalization. I wanted to normalize. So when you wanted to download, I'm just telling to my model I wanted to normalize the architecture. So normalize the inputs between the range of mean and standard deviation as a point. So likewise, it will be taking those data set from out of 60,000, it may download 50,000 of data which represents the mean and standard deviation of this condition. Now I have transformed the data set. Now I download the data set in the object of MNIST. So data set part is almost done. Now I need to split it. So now I downloaded the data. Next I need to load the data set. So by using this data loader function, I'm loading the data set and creating the object. That's it. So data set is ready. So now data set is ready to give it to the architecture. Next one is the loss functions. We need to define the loss functions for your generator as well for your discriminator. So I'm defining like a binary cross entropy. So the binary cross entropy I'm defining it for discriminator, since it is a binary problem statement. Binary classification, defining like a binary cross entropy. And the next one is I'm defining the Adam optimizer, and the Adam optimizer for the discriminator as well as for the generator. So here also I'm keeping as an Adam optimizer and the Adam optimizer here as well. Okay, so the learning rate data last time I have explained you something. Okay, the same thing. So I have defined the loss and as well as optimization. And next one is like a epochs. So how many epochs I wanted to do this is 50 times. The entire back propagation I wanted to do for 50. Back propagation of 50 times. Okay. And the next one is like some of the Pythonic steps. It's nothing but steps and the critics about the Pythonic steps. Now you can see. So now, if you see this code, now my construction of the architecture is done. Define the inputs, download the data set, define the inputs, and the next one is like I have defined what is the loss function and what is the optimization technique. Everything I have defined, everything is there. Now, all I need to do is I need to kickstart the model. Before I kickstart the model, I'm just doing one thing is nothing but defining the labels, discriminator labels, and as well as the discriminator original labels, the fake labels. This is nothing but what I'm doing in the sense I'm creating some samples. I'm creating some dummy data in order to make the comparison during the time of loss calculations. Okay, so that's what I'm creating some dummy data. So I'll tell you where we are using. So now we have defined the dummy data also for ground original data for the fake data. Now in the for loop, this is a for loop where the execution is happening, the one which I told you, right? I told you that I'm a generator, you are the discriminator. I told you that we have to go for 50 inputs, 50 backpropagation I want to go for. Initially I'll generate the images and you will compare it with your ground truth and you'll be giving the feedback. Based on your feedback, I'll be enhancing the architecture and you'll be giving other set of images and you'll be revalidating with the ground truth and you're giving the data. So this iteration will go till 50 inputs. That is the same concept is happening within this form. Okay, in simple words I can explain. First, maximum epoch 50 epochs. Okay, I'm taking the first epoch. I'm taking in the first epoch I have a data loader almost 60,000 of data is there. Consider I have a 60,000 of data. So first images I'm taking. Okay, just consider first images down to data. So now I'm calculating the image. This is the down to the image. The ground truth image I'm giving to the discriminator. Now I have a discriminator output. Okay, for the real samples. Now I need to calculate the loss. In order to calculate the loss, I need to compare the result with some original data. Since it is my ground truth data, so I need to compare with the D labels. That means the fake samples I have created, right? And just we can ask, so why we have to compare this one? This may create some chaos, right? Of course, it will make some chaos, but we have no options in order to calculate the loss function because generator is not generating the images so far. So that is why. So still, that's what I'm comparing with the D labels. Now I'm calculating the loss for discriminator ground truth data. For discriminator takes two data. One is the ground truth data and another one is like a generated sample. So now I calculate the loss for discriminator ground truth data. Guys. Alright. Or passcode Alright. So now coming to the point. So this is a loss for discriminator of ground truth data. Next one is like I have a randomized data and in a noise data. For this noise data, I am giving this to the generator. The generator will give the results that will be given to the discriminator. So now what will happen in the sense? We have given the noise data. That noise data 100 samples will be given to the generator. Generator will give you the generated fake samples, right? That will be given to the discriminator. So now I have the final output. That means this is a place D of G of Z. That output is given some output. With respect to that output, I need to calculate the loss with respect to fake samples. So that is what I am using this output for comparison. I am using the fake samples, fake mock data. So now I am comparing. I got the loss calculation. So now I have the loss criteria. Now in order to accumulate the overall loss for the discriminator, I need to accumulate this one and this one. As I have shown in the presentation, now I have a discriminator loss. Okay, now I calculate the discriminator loss. So by seeing this, you can able to understand one thing, right? We are just running first discriminator first. That means we are not generating, we are running the generator first. That means we are making discriminator to run first to understand the ground truth data. So based on your feedback, I can able to generate the new data. Randomly, I cannot generate some data. Okay, that's what I'm triggering the discriminator first. Now discriminator ran completely. And the next one is I'm setting the zero gradients. Before model runs, I'm setting the zero gradients. I don't want any specific weights to be calculated. And I'm doing the backward calculation on each and every steps. The steps based on the bag sizes. Okay, now if it is done, next it will go to the generator. So now maybe when you have a time, if you have a time in the sense, print the entity, so that you can able to understand what specific key technique I have used to generate the images. Because I'm not running the generator for all the times. Based on some step, based on few steps, I'm just running the generator because running the generator will take most of my time and the Google Colab will fade away and it will fail again. Okay, that's what I have made some Pythonic stuffs right here in order to define when generator needs to run and when discriminator needs to run. Okay, this is some of Pythonic stuff, it's not a standard technique. So now I am generating the generator. So for generator, I am giving the samples. That sample is given to the discriminator overall output. By using that output, I am comparing with the ground truth data. So now I am getting the generator loss. Because generator should compare with the ground truth data to get the original result generated or not. So I have a generated loss. And now again same back propagation, and as well as setting the zero gradient. Now this flow will happen like anything. For one epoch, consider for one epoch, it is running for 1000 steps. For one epoch, we are running for the 1000 steps based on the batch sizes. Okay, so now if it is a 500 step in the sense I wanted to print something, and if it is a 1000 step in the sense I wanted to generate the outputs. Because for each and every epoch, this particular architecture may run beyond the 1000 steps. So I don't want to run, because if I run in the sense my Google Code, I cannot able to show the output in this Google Code. Sure, Google Code. That's what I'm limiting it like a maximum 1000 steps for one epoch. Okay, so now also you can see the output. In this output, for zeroth epoch, maybe you can see the zeroth epoch, the loss and the G loss, D loss and everything. So this is for 500 steps and 1000 steps. So every epoch will have a 1000 steps, and I'm defining it between the 500 step, between the 1000 step, give a heart and show me like what is the losses navigating between them. So like this you can able to see epoch 1 we have a 2 results with the 500 step and as well as a 1000 steps like this. Okay, so this is nothing but what I'm trying to do here in the sense I'm generating the samples of an MNIST data set. My data set is a less weight model, so that I'm just limiting it out. I wanted to run it for few steps, few batch sizes, but I don't want to run for all the steps. I don't want to execute for all the steps by exclusively handling the batches. And if you wanted to mute it, you can able to mute it, but with respect to Google Colab, you can able to run maximum 40 minutes with the free version of the Colab. Maybe if you have a Pro, maybe you can able to run 5 hours, 6 hours also. Maybe if you have a Pro version, maybe you can try with changing this steps and everything. You can able to, maybe you don't need to set the 1000 steps or not, just to skip it over again. Once the first epoch is done, and then you can generate a sample. Likewise, you can able to do. And if you make the changes in the code in such a way, you can able to see the exclusive results and exclusive output too much. Okay. Is it clear? Any doubts? There is any doubts on this? You can use the same data. You can able to use the same source code for any kind of data sets. I have tried only with the benchmark data set, and you can replace with your own data sets, and you can need to change some of the resolution changes and all you have to do. Once you make the resolution changes, you can able to generate a lot of images and videos also. And the same thing, I have used it for the color images. If you see the color image, C for 10, I have tried only with the vanilla. For vanilla, since I'm using a C for 10, you see, I'm using the resolution, each and every image resolution is a 32 cross 32 in C for 10, and channels is a 3. So this is the one simple changes I have done, and I have also increased the canvas size, the output size, in order to accommodate this setting everything. And also, in the discriminator, you see that I wanted to generate the 3 sample images, 3 channel images. The images with the 3 channels. Under the generator, also when I'm generating the final output, I wanted to have a 3 channels. That's it. That's what. The source code which I'm explaining you, which you understood in the sense, you can able to do any kind of GAN architectures by using the knowledge of the one source code. Almost everything is similar. Almost everything is similar. There is no new strategy or something else. Maybe.
How to set that kernel size? Sometimes we are using 20 plus to 28. That is our wish to set whatever the kernel size.
No. This 32 plus 32 is not kernel. Actually, this is about the image size. In C for 10, we are having almost 60,000 of picture. Each picture size is a 32 cross 32. In MNIST data set, I have shown 28 cross 20. So that means each and every image size of the MNIST data set is a 20. So I wanted to generate the image in the same resolution. That's what the 32 cross 32. And if you go for CNN architecture, right, there you can able to define. So what is the kernel size you want to do? So big kernel size, you will be having the big convoluted features. And if you have a small kernel size, and you will be having the small convoluted features. And then that's also, if you are having a big kernel size, it will eat most of your computational powers. So that's what we will be starting with the 3 cross 3, because since it is a smaller, it will take the process very fast. So guys, any doubts? Okay guys, maybe you can occupy the machines, maybe you can try running the source codes I have taught you. So one is a GAN defect and another one is like a this amnesty data set. Maybe you can occupy the machines and we can try it out here also. We can lunch break I will give you at 12 o'clock. So the next session will begin at 1 o'clock. So I will not be there and one of my friends will join. Mr. Deepak, so he's the one who will be attending the next session. He will be joining at 1 o'clock and we will take the session. Okay, so okay, you can disperse now and you can take the machines and you can run the same source codes by your wish. Okay, and if you face any issues or something else, you can call me and wish. Lost generator lost but generator lost observe generator lost discriminator lost so what is the output Guys, you can take the machines and you can practice it. A source code which we have seen, right? Just disperse and go to your occupy some machines and practice something else.